Yeah, okay. That worked better than had it. Okay, well, we're back. I'm gonna have to do this kind of quick because we never know when Zoom is gonna do this, and maybe you have to look at the videos if I'm going too fast for you. So we've got these points, and I think we were okay there. And we've chosen to go through this point, then this one, and then come up and turn around here. And that's going to be the graph of our polynomial function. So we can easily do something like that. So now what do we know? We know that P of X has to have factor X plus 6 in order to go through -6, 0. Has to have factor X minus 2 to go through 2, 0, and X minus 5 to go through here. Except that if that's all it has, it's going to go straight through here because X minus 5 will just take it straight on up and it won't go down over here. Okay, now as we talked about last time, that means that this thing's acting like a parabola here, so it's acting like X minus 5 squared. Okay, you know, your toolkit squaring function shifted over 5 units is going to have vertex here. If you flip it upside down, it'll act like this. And at least for a little while here, very short while, it's going to act like a parabola. Okay. And it's not going to act like a parabola unless you got a square on it there. That's the whole thing of multiplicity. So you got rules for multiplicity. There's a reason for the rules, and you know enough about toolkit functions and transformations to understand that reason, which means you're more likely to remember the rules and understand what you do more deeply anyway. So I advocate that you understand why that's true, if at all possible. But you do have the rules, and the rules are sufficient to get by, okay? And if that's the best you can do, it's still pretty good. If I ask you to explain why that has to be multiplicity 2 in order to do that, it would be for extra credit. That's going to require you to know that. Okay, well, the other thing is, if I plug in X equals 0, I get 6 times -2, which is -12 times 25. Okay, and that's 300. Well, pretty close, 386. I must have been smart when I figured that number out. First time in my life. They were smart. Okay, I was just lucky. Gremlins were with me that time. Okay, so you got this. And everybody got to this point more or less. Some people kind of forgot that multiplicity thing, so make sure you understand it. Make sure you at least know to do it. So now what do? We've got everything but the value of A. So now we plug in coordinates to the known point, which of course are 0, 386. Once we do that, we're going to be able to solve for A. I'm not going to do all that arithmetic. I'll give you a ballpark if it might be right or not. So we get 0 equals A times 386 plus 6 times 386 minus 2 times 386 minus 5 quantity squared. Now I'm going to make a guess. This is pretty close to 400 times 400 times 400 squared, right? Which would be 400 to the 4th power, which would be 4 to the 4th times 10 million. Well, 2 zeros, 100 million. Okay. So it would be about 256 times 100 million is 25 billion. So I'm going to say it's about 18 billion times A. And wait a minute. See what happens when I get in a hurry. Not blaming Zoom, I think it's an internet connection. Let me do it right. Okay. When I plug in I'm going to plug in 386 for y, not for x. Okay, so we get 386 equals a. It's too bad. I was really looking forward to doing that arithmetic. It's 386 for y and 0 for x. So that's going to be 0 plus 6 times 0 minus 2 times 0 minus 5 quantity squared, which I think is 300 times a. Okay, pretty sure about that 300. So this is really an easy step if you just think to do it and understand what's going on. Okay. Especially if you've got the y-intercepts, you can use zeros here. So a equals 386 over 300, which is 193 over 150. And I don't think it reduces any more than that. I'm pretty sure if I will, yeah. Okay. So we just replace a with the value of a. And there we've got our P of X function. And if you practice it a little bit, it's not at all difficult. You just got to remember to do everything. And if you haven't done enough problems, you're not likely to remember. All you got to do is do enough problems. Nothing particularly difficult about this. Most difficult thing be understanding why that has to be a parabola. But you don't have to understand that. Okay. Again, it's good if you do, but know the rule. The multiplicity is 2, it's like that. And of course, if the multiplicity is 3, what's it look like? It looks like the cubing function. You've seen it. Open Math does it. I didn't do it in class because I knew you'd see it in Open Math and it would be explained there. Okay. And you'd be doing it under duress because you're doing your homework. Okay. So that looks pretty good. And y'all are doing pretty well with this. Okay, now we haven't covered rational functions except for the little blurb at the beginning of class. So you don't have to worry too much about how you graph this thing. I'm just going to show you how you use long division because long division is one of your assignments and it's a good example of long division. And there's also a little more to it that will do you some good in a week when you have an assignment in rational functions. Okay, so you got this rational function. Okay. If we divide x squared plus 2 into x cubed minus 6x squared plus 9x minus 5, what are we going to get? Well, x squared goes into x cubed. Well, you ask yourself, what would I have to multiply by x squared to get x cubed? It's going to be x. So now we take x and multiply by this, and we're going to get x cubed. And I'll write it out the way I don't want to write it out. And we get 2x. Now, what's wrong with the way I wrote that out? Somebody want to tell me? Hang on a second, let me pause. Okay, so I got 2 good comments there. One is I need to put little minus signs here to remind myself that I'm subtracting, right? The other thing is I can't subtract 2x from 6x squared. Okay, yeah, the result would be different for different values of x. We want a result that's true for all values of x. So I don't want my 2x there. I want my 2x over here. Well, yeah, all the way over here. And then I want a minus sign here and a little tiny minus sign reminder here. Okay, and of course it's x squared plus 2x, but really we're going to subtract it. Okay, now really what we're doing is we're subtracting x squared plus 2x from the whole thing up here. Okay, well, we've got nothing to subtract from the 6x squared, so we just end up with a negative 6x squared. Now, when we subtract 2x from 9x, we get 7x. And then we get minus 5. Okay, well, that's perfectly okay. But it looks a little weird because we don't have anything there. No, open math might tell you to put a 0x there. Okay, that's perfectly valid. But if you just understand that you're subtracting x cubed plus 2x from whatever is up here, and that you've done that so that the x cubed will go away, then it's going to be okay either way you do it. So I'm going to do it this way. Okay, anyhow, then x squared goes into minus 6x squared minus 6 times. And then we get minus 6x squared and minus 12. And now we're going to subtract all this. So we better put a little tiny plus sign here to remind ourselves that to subtract these negatives, we've got to actually use a positive. And of course, this goes away. And we end up with 7x plus 7. Boy, that's 7 times the quantity x plus 1. These x plus 1s keep getting me today. The MDE class could tell you why, or if you look at the video we did. Anyhow, it's 7x plus 1, okay? Now, we could write that as r 7x plus 7, 7x plus 7, and 7x plus 1. Or we could write that as plus this divided by x squared plus 2. Okay. So this means, since this divided by this is this, that this rational function here is equal to just plain old x minus 6 plus 7x plus 7 over x squared plus 2. Okay. Now that's going to be important when we do rational functions. We can graph this without having to graph all the rest of what we need to know about rational functions. Well, if x is big, then x squared is way, way, way bigger than 7x. Like if x is 1,000, your denominator is about 1,000,000. Your numerator is only about 7,000. Okay, so this is like 0.0014 here. Okay, so this becomes insignificant as x gets large. Graph of x minus 6. Here, where this line is y plus negative 6. That's x-intercept. And if you want this line is x equals 6. That gives you kind of a scale. And then you got to worry about 7x plus 7 over x squared plus x. Now, 7x plus 7 is 0 when x equals 1. So the graph of 7x plus 7 has a 0 here. And it's negative over here and positive over there. So it's going to have a graph that kind of looks like this. And you don't have to worry about why. I'm just telling you what I think it looks like, okay? I think it looks like something that has an asymptote at the x-axis. Comes down a little bit, comes up a little bit, and then comes back with an asymptote here. So basically it's 0 from here to here, 0 from here to here. It's got a little wiggle right here. meaning that this function has a graph that pretty much matches this, but it's got to wiggle down a little bit here and then wiggle up a little bit here before it goes on. So this orange graph is y equals 7x plus 7 over x squared plus 2. And it's not as symmetric as it looks, but I'm not going to belabor that point. And this is y equals x minus 6 plus 7x plus 7 over x squared plus 2, which equals x cubed minus 6x squared plus 9x minus 5, all divided by x squared plus 2. This is equal to this because of this. And that's the main point I'm trying to make right now. It has an implication for the graph, but this is one way we might ultimately be using the long division to get a handle on a graph that would otherwise give us bits. Okay. So if that halfway makes sense, great. If it doesn't, just focus on the fact that here's how we divide. And when we divide, whatever's in here equals whatever's up here times this. Suffice to multiply all this out. Okay. I'll put this over common denominator and all that stuff. I would end up with this. Okay. Now everybody seems to be doing real well with this. You get x equals -3 plus or minus the square root of 9 minus 36. I'm not writing out all the details. And we can write that as -3/2 plus or minus the square root of -27 over 2. Now, what are you going to do about the square root of -27? Well, you should remember from your prerequisite courses, and we've also talked about it in here a little bit, that's, let me just point this out, the square root of -27 is the square root of -1 times the square root of 27. Okay. Square root of -1 is I, imaginary number. Everybody's familiar with that, aren't you? Anybody has never seen that? Yeah, in Algebra 2 course, even in Algebra 1 course, you use the quadratic formula. You should have seen it. Maybe somebody found out it wasn't on the SOL and didn't do it. Okay. I mean, that could happen. If they knew it wasn't going to be in the SOL, why cover it? But just because you're going to need it later. That's the flaw of the SOL. But I'm not sure it deserves that specific criticism. Okay. And then the square root of 27 is the square root of 9 times the square root of 3. If we want to factor out every square we can out of this number. Okay. And often we'll write that as 3 square root of 3 with the I on the end. So that this becomes -3/2 plus or minus 3 square root of 3 I over 2. Okay. Now what's I? Well, I is defined to be the square root of -1. It's not real. It's imaginary. Now, as it turns out, imaginary numbers don't appear to be totally imaginary, because it appears that you can't really do quantum mechanics without them. Quantum mechanics is the most successful, although very difficult to understand, theory of the universe that anybody has. It's never been proven wrong. It's never been proven not to predict things. So you don't have to understand that. You got to go way deep into physics to do it. I is your imaginary number. Okay. I also spent 2 years of graduate school going deep into this stuff. Deep enough that I scratched the surface. Because it's really deep. Okay. And I did pretty well with it too. Functions of complex variables gets very complex, as you might expect. Okay, well, those are near and dear to my heart, but for you, it's I. And when you square it, you get -1. It might be that if you haven't seen it, you really need to do some work with complex numbers. But I'm going to do a little bit with it right now. And well, that means exclusion has an imaginary part, so it isn't pretty. It doesn't mean it's not important. Doesn't mean it's not really powerful. Okay. You can ask any of our second-year engineering students why this is important, and they could give you a fairly good answer. They wouldn't understand the thing about the quantum mechanics, but they had a course in what's called differential equations where they had to use this all the time. It makes certain physical problems much easier to solve. Okay. It's very handy, including being apparently indispensable. Okay, so this is a complex solution. And I should say solutions have imaginary parts. Because there are two solutions, one for plus and one for minus. Okay. Now, given that not everybody's actually seen this, you need to think for a second what I need to do about it, on how I need to approach it. Well, let's just store this away for a minute. And let's take the expression for the function. Take p of x equals x cubed plus 7x squared minus 5x. And then let me do a little figuring. And then okay. Now what I'd like you to do is this division. Take a minute, see what you get when you divide that out. Which I see. Okay, pretty much I see good progress on this. So everybody's either done or getting close to, almost everybody is. Okay, so I'm going to have x squared here because x squared times x gives me x cubed, and x squared times -2 gives me -2x. Which means if I, well, never mind, I'm going to say that. Okay. remind myself that we're subtracting this. So we put the plus signs on it and we get 9x squared minus 5x. So we get made it minus 9x here because minus 9x times x. Why is it minus? Some secret would bad. There we go. Plus 9x times x gives us 9x squared. So we're going to have all our x squareds accounted for. And then, of course, we're going to multiply that by the -2. Be careful about our signs. And we get 13x minus 26. So this gives us plus 13. Now 13 times this gives us 13x. And we subtract this. And we get 0. So it's no remainder. Okay. Now, why is that a good thing? Well, we want to factor this. Remember that we don't know much about a polynomial unless we factor. And we just started our factorization. We get x minus 2 times x squared plus 9x plus 13. Because, of course, this times this equals this. That's all I'm saying here. This times this has to equal this. That makes sense? So that kind of slick. It's kind of. You can use long division, and your open math will even show you how to do synthetic division, which is a more efficient way to do long division, but it is a little further from what's really going on, so I don't even bother teaching it. Okay. We just do long division, but if you're doing a lot of this, synthetic division is useful. If you turn out to, well, never mind. Okay, so anyhow, okay, now what about this? Well, we find when this is 0, because we know the zeros of a polynomial, then we can write it out in factor form. Well, I did my arithmetic right. There's a solution. Notice the solutions to quadratic equations come in pairs because of the plus and the minus. And somebody's telling me that I messed something up. Did that quick so I could. Okay. Again, solutions come in pairs, one with plus and one with minus. Okay. So now this quadratic function is x minus one of these zeros times x minus the other one. I think that's time I just read. Oh, we're still there. Okay. Or is that my computer, somebody else's? It's mine. Okay. I don't know what it's telling me. I don't want to know. Okay. I hate those sounds. Some people like them, find them pleasant. I think Microsoft set them up so they'd be pleasant. They just irritate me. If you find them pleasant, that's okay. Find them irritating, that's okay too. Okay, well, why would I write this? It's because if I want to graph this polynomial, its zeros are going to be these. So one of the zeros is -9/2 plus the square root of 27/2. And the other is -9/2 minus the square root of 27/2. So that the graph of this polynomial x squared plus 9x plus 13 looks like this, with a 0 here and a 0 here. Now, if you had polynomial with a 0 at -5 and a 0 at -2, you would know that that polynomial has an equation like y equals x minus, well, it'd have to be x plus 5 times x plus 2. And then maybe times some constant a. Because where is this polynomial 0? It's 0 when x is -5. It's 0 when x is 2. Where's this polynomial 0? This polynomial in this form. When is this 0? It's 0 when x equals -9 plus the square root of 27/2, because you'd have -9 plus the square root of 27/2 minus that expression. And when it's here, same thing. If you plug this in over here, you're going to get 0 on this one. Okay, so it's just a 0 property. What this has to do with complex zeros. Now, this didn't come out with a complex 0, but if there had been an I on this, okay, we'd still write it this way. But this thing, you know, this number here would have an I on it. Okay, so probably I can find a little board space quickly. Do one like that, but I don't have any board space. No time to clear a board. Got a little space here. Kind of squeeze it in. Okay, but let's say we have another polynomial. P of x that we determine to be x plus 5 over times x squared plus 2x plus 4. Your zeros are x plus 5 equals 0, so x equals -5. And at x squared plus 2x plus 4 equals 0, which means x is going to equal -1 plus or minus the square root of 4, 16, 12. The square root of 3i, I think. Okay. So there are 3 zeros. So u of x, to have a 0 at -5, it has to be x plus 5 times something. Of course, we already know that. Then times x minus -1 plus the square root of 3i. And then x minus -1 minus the square root of 3i. The point now is your complex zeros come in pairs. So if I know that -1 plus the square root of 3i is a 0, I don't have to do any work. I already know that -1 minus the square root of 3i is a 0. So that's a statement you take to the bank, and that should be very helpful with the homework assignment. If you haven't ever seen complex numbers, don't know how to multiply them, add them, and divide them, please email me and I'll send you an exercise. It is particularly difficult, but you really need to know that, okay? Or if you want a refresher on it.